Base-catalyzed mechanism of aldol condensation. In the experiment, one equivalent of the ketone is reacted with two equivalents of the aldehyde to form an alpha beta unsaturated carbonyl compound. This compound is the aldol condensation product, which is a bigger structure than the original ketone and aldehyde. The aldehyde is color-coded, it's blue. In the final structure, which is the aldol condensation product, the carbons colored blue are coming from the two aldehydes. The base, sodium hydroxide, will abstract the hydrogen in the alpha carbon, which is acidic, forming a carbon ion, releasing water. The carbon ion has a resonance structure, shown below, which is an enolate. There is a carbon-to-carbon double bond and an O-. The carbon ion will attack the carbonyl carbon in aldehyde, which is partially plus, forming a condensation product. The new carbon-to-carbon bond is this bond. The O- will abstract the hydrogen and water, releasing OH-, forming an alcohol. Another hydroxide will abstract the hydrogen and the alpha carbon, releasing water, forming another carbon ion. This carbon ion will attack the carbonyl carbon of another aldehyde, forming another new carbon-to-carbon bond, which is this bond. The O- generated will abstract another H in water, forming now a diol. So two alcohols in one structure. Two hydroxides will abstract the two acidic hydrogens in the alpha carbon, releasing water, and then this bond and this bond will form an alkene, two alkenes conjugated to the middle carbonyl carbon. The OH is now released, two OHs, and this step is the dehydration step, eventually forming the aldol condensation product, which is the alpha beta unsaturated carbonyl compound. Experiment today is about aldol condensation. We are going to mix an aldehyde unknown and then a ketone unknown. So typically each student will set up two combinations, so you will have two pairs. I'm illustrating one pair. So an aldehyde and a ketone, and the unknowns are labeled as A for aldehyde and then K as ketone. You will get one vial and it's numbered. So for this case, I'm doing A15, that's an aldehyde number 15 unknown, and then ketone 33, that's the ketone unknown. So the experiment is you are going to make a combination, and then you are going to identify at the end what is the aldehyde and what is the ketone. So the aldehyde is going to be in excess, the ketone is going to be in lesser amount. So the aldehyde is 4 times the amount of ketone. And then I also have here 2 molar sodium hydroxide. So we need a base. That's 2 molar sodium hydroxide. And I already measured in a graduated cylinder 3.8 ml of the 2 molar sodium hydroxide. And we have a solvent which is 95% ethanol. And then we are going to mix it in here. So 4 things we're going to mix: aldehyde, ketone, a base, and then ethanol as the solvent. So I have an RBF 100 ml round bottom flask, and then a magnetic stir bar inside, and then a stir plate. I got here a graduated pipette, and this is calibrated. So it's a graduated pipette, and up to here, up to this mark, it's a 1 ml. So I need to deliver 1 ml of the aldehyde. So I'm gonna withdraw up to here using the pipette. And then, so this is our aldehyde unknown, 15A or A15. So our aldehyde unknown is A15. So I'm gonna pipette, I'm gonna withdraw a ml. So I'm trying to avoid the bubbles. Okay, so that's about a ml, and then I'm gonna put it here. Okay, so I delivered a ml, and I'm going to save this pipette. That's why I labeled it as A15, just in case I need to redo. And then I'm going to add now the ketone, which is in this case unknown K33. And then I'm going to use this pipette. So remember, the amount of aldehyde is 4 times the amount of the ketone. So I marked it here. That's 1/4 of the 1 ml, 0.25 ml. So the aldehyde was 1 ml, and this one is 0.25 ml in this mark here. So the ketone is unknown 33. So I'm going to deliver only up to that mark here. Okay. And I also label it as K33 just in case I need to redo. Okay. So I turn it upside down like that. And then I'm going to add the sodium hydroxide 3.8 ml. So I'm going to use this pipette. So that's sodium hydroxide 2 molar. So I'm done with the base, and then I'm going to add 5 ml of the ethanol, 95% ethanol, and then again, so 5 times of 1 ml. That's 1, 2, 3, 4, and then 5. Okay. So I'm done with that one, and then I'm gonna stir it. Okay, so the stir bar is stirring. I'm going to stir it for 15 minutes. I cork it lightly so that no particulates go into my solution. And now I'm stirring it for 15 minutes. So you can see already some precipitation. The product is going to be a solid. It's actually colored. So we started with clear solution. So we started with clear aldehyde and clear ketone, both liquids, and then we are going to get a product which is actually colored, and it's going to be a solid at the end. I stirred the reaction for a total of 20 minutes, And you can see that you can see chunks of precipitate at the bottom, yellow, orange in color. So now I'm ready to filter, do vacuum filtration, and I'm gonna turn off the stir plate. Turn off stir plate, and then I'm gonna take it out. So take note that I did the reaction under the bench hood in here. Okay, so now I'm going to take it out and clamp it. I have the flask sitting on the cork in here. And now I'm ready to filter. So I'm going to wet the filter paper. There's a filter paper in the funnel. And I'm now going to apply the suction, the water aspirator. And then just to make sure that it's flat filter paper on the Buchner funnel. And now I'm going to filter this out. And then I'm going to rinse it with ethanol. So I'm squirting the mouth. I squirted the mouth of the RBF, and I'm not touching the mouth with the tip so that I don't contaminate my solvent. So I kind of swirl it around and then pour, and then do again a few times. Okay, so you see that the color actually of the solid is like there's yellow and there's also orange kind of coloration on the other chunks of the precipitate. So we're gonna do some cleanup. So I'm gonna take out the suction, the water aspirator. And the next step is to do some cleanup. And then I'm going to, remember there's a base when we did the aldol condensation. So I want to neutralize it with an acid. So in fact, I have in here a solution of 4% acetic acid and 95% ethanol. And I already measured about 10 mL of it. And I'm going to transfer this sample into, so I take out this stir bar and I'm just going to transfer because I want to clean up the sample. I want the color to be as even as possible and clean it up before we do the melting point determination. So we have quite a bit, and we only need a little bit of sample for the melting point determination in the capillary tube. So we have plenty of solid to use to determine the components. Okay, so I'm gonna crush it. Actually, I can use also the glass stirring rod, and then I'm gonna add now the acetic acid in 95% ethanol to kind of wash out whatever impurity. And then I want to crush it so that I expose the solid using the acid because there is a base. So now I crushed the chunks of solid precipitate at the bottom, and now it's uniform in color. It's actually bright yellow. So I'm going to chill it a little bit in ice water. Few minutes, and then we're ready to filter again. So that is our product. So we synthesized a new molecule composed of an aldehyde and a ketone via aldol condensation reaction. So we let it cool, and then I'm going to filter. So I changed the filter flask. This was the original filter flask. So I have a new one. And we are going to filter it through. This was the old filter paper, and this is now a new filter paper because I want the sample to be as clean and as pure as possible for the next step. The precipitate or the solid sample, after I chilled it, looks like this. It's still chilling, and then you can see that it's now ready to be filtered. So I have again the setup in here for vacuum filtration, and I'm gonna moisten the filter paper. So I have a fresh filter paper inside in here, and then I will now moisten it so it's flat. Okay. And then have the water aspirator running. And then now I'm ready to pour the sample. So I'm using again 95% ethanol just to rinse out any impurity that's still stuck. So I'm just gonna crush the big ones. So I want to rinse it out with ethanol more. Okay, I did not lose a lot of solid going through, but anyway, we actually just need a few samples for the melting point determination. Okay. And I'm gonna detach the water aspirator off, and that is now our sample. So we're gonna dry this. Okay, so we are going to dry this till next lab period for another week, and then we are now going to do the melting point determinations. That's our sample. The aldol condensation product, after a week of drying, it's yellowish in color. It's deeply colored yellow. And I'm now going to scrape it from the filter paper and then transfer it into the vial. So I put the sample into the vial, screw cap vial, and now we are going to take the melting point of the sample. Melting point determination of the aldol condensation product is the next step. So I took a capillary tube from this container. The capillary tube is closed in one end and then open on the other end. So I'm going to pack this capillary tube by scooping in the open end some of the samples. And then, so I'm going to scoop a little bit. So it's kind of fluffy, the sample. And then I'm gonna get again, a glass tubing open in both ends. And then I'm gonna drop it so that I pack in the closed end. So drop it one more time. And I should have enough sample. So I should have enough sample for the melting point determination. This is now the melt temp apparatus. I put the sample inside. So we want to determine the melting point of the sample. So in the table of the combinations of different aldehydes and ketones, the lowest melting point temperature is 98, and then the highest temperature is 235. So you have to start at 98, you ramp it to 98, and then slowly increase it depending on the temperatures. You have to look at the numbers in the table so that you are not overheating it. So otherwise you will miss the melting point. So I will start with 98 by pressing plateau set and then press this together to 98. And then I will start heating. And then start heating. So it's going to go up, and then you have to look through this eyepiece and then determine if the sample will melt. meaning that it's going to change from solid state to a liquid state, and it should be sharp. So sharp means that the sample is pure, narrow, melting point range, and then sharp, and then close to that value in the table. You are trying to determine the melting point of the sample, and then you are going to finally determine the structure of the original aldehyde and ketone that we mixed together at the beginning of the experiment. The sample did not melt at 98, so we are going to set it to the next temperature, to the next melting point range in the table, so that's 113. So how you do it is you stop, and then you again press plateau set, and then go up to 113, and then again start. So it's gonna go up to 113, and then we are going to check if the sample will melt at that temperature. The sample melted at 112 to 113. The solid sample, which is yellow, now melted, and it's still yellow in the liquid state. So we don't have to heat it further because we already have the data for this particular combination of aldehyde and ketone. So that means that we don't have to increase the temperature to 118, which is the next melting point range from the table. So for this sample, it's done because we found the data already for the melting point, and now what we're going to do is we are going to match it with the aldehyde and then the ketone in that table, and then determine the identity of the aldehyde and ketone based on the melting point data that we have right now. So if I take out the sample really fast, you can see that it's actually a liquid. But it will solidify fast because, see, the room temperature is lower than 113 degrees C. This is now our product from the aldol condensation reaction. And I put it in a screw cap vial. And it's now A15, which is the aldehyde, and then K33, which is the ketone. So this is the original aldehyde labeled as 15A or A15. And then this is the ketone K33. So then we had a melting point determination, and the melting point of the condensation product from the aldol reaction is 113 degrees C. So based on our melting point data, we have, for the example that I showed, the melting point was 113 degrees C. So therefore, in the table that I put in the handout, it's going to be this data, 113. Therefore, the combination is benzaldehyde and acetone. So each one will be provided a melting point data, and you will determine what the combination is for the aldehyde and ketone. So you will be given two melting point data. You will figure out what the starting aldehyde and ketone in the mixture. So the choices for aldehydes are below. It's going to be either benzaldehyde, 4-methylbenzaldehyde, 4-methoxybenzaldehyde, or cinemaldehyde. So it's going to be either benzaldehyde or derivatives of benzaldehyde or cinemaldehyde, which is E3-phenyl 2-propanol. The choices for ketones are below. It's going to be either acetone, cyclopentanone, cyclohexanone, or 4-methylcyclohexanone. So the aldol condensation product is actually a big structure. It's colored, like in this case, it's actually yellow, and it's a solid. So the starting aldehyde and the starting ketone are liquids at room temperature, as shown in here. So 15A and K33 are both liquids at room temperature. However, the condensation product is going to be a solid, and it's colored sample because it's highly conjugated. So it's going to be either very bright yellow or orange in color. These are different samples of aldol condensation products, and they're all solids, and then they are all deeply colored. So for example, this is a combination of benzaldehyde and cyclohexanone. And then benzaldehyde and 4-methyl cyclohexanone. So the aldehyde in those two samples is benzaldehyde, while the ketone is different, it's cyclohexanone, and then the other one is 4-methyl cyclohexanone. The next 4 examples in here are all the same aldehyde, and that's cinemaldehyde. So cinemaldehyde plus acetone, and then cinemaldehyde plus cyclopentanone, cinemaldehyde plus cyclohexanone, and then cinemaldehyde plus 4-methyl cyclohexanone. So depending on the ketone that you're adding on cinemaldehyde, you will have a different range of color. So it's ranging from deep yellow to about orange or rust-colored sample for this example in here. So again, they're all conjugated structures, and that's why it's colored, and also we created a bigger structure or bigger molecule. That's why the sample is now a solid, and we started with both liquids. The aldehyde is a liquid, and then the ketone is also a liquid. So for the experiment, you are going to identify what the identity is of the aldehyde, and then as well as the ketone. Assignment of unknowns for the class and melting point data. The unknowns are assigned according to last names listed in this table. For instance, if your last name starts with A to D, your unknown is A1 plus K1. That combination will form an aldol condensation product with a melting point range of 179 to 181 degrees C. The second unknown assigned for those last names starting with A to D is going to be A2 plus K2. In the aldol condensation product formed from that combination will have a melting point range of 97 to 99 degrees C. The other last names, you will follow this list and the corresponding unknown combinations. A stands for aldehyde, K stands for ketone. From the table listed in the handout, you will be able to figure out, based on the melting point range, the corresponding aldehyde and ketone for the unknown. Lab report for experiment 7. Part A results. Based on the previous slide, each one should have 2 unknown number combinations with the corresponding melting point range. From the melting point range, you should be able to identify the aldehyde and ketone for that combination. So you should have 2 aldehydes and 2 ketones. Part B, reaction mechanisms. Draw the structures of the 2 aldol condensation products based on the identified aldehydes and ketones. Then write out the mechanism for one aldol product or one combination in the presence of sodium hydroxide, as shown in the experiment. This is a base catalyzed aldol condensation. So select one combination, either the first one, this aldehyde plus this ketone, or the second one, this aldehyde plus this ketone. For the same combination that you pick to write out the base catalyzed aldol condensation, write out the mechanism for an acid catalyzed aldol condensation reaction. So two mechanisms. The first one is base catalyzed. The second one is acid catalyzed. This is the final lab report for experiment 7. In the experiment, each one is assigned a specific ketone and an aldehyde. Based on the melting point determination, you should be able to determine what is the actual starting ketone and aldehyde. Then for the mechanism, which is being asked in the final lab report, you are going to follow what I've shown in here, which is the mechanism of aldol condensation. However, you have to substitute what the R group is for the ketone and the aldehyde. So in this mechanism in here drawn, the aldehyde actually is color-coded. It's blue. So for example, in this structure, this part here, which is blue, and this part is coming from the aldehyde because you have two equivalents of the aldehyde. So follow this mechanism to be able to write the actual mechanism for your actual structure of the ketone and the aldehyde in the experiment.